Hi everyone. At the end of the first lecture, we have proved that in a given algebraic function field, evaluation ring is also a local ring. That means it has unique maximal ideal P. And we see that X in P if and only if X inverse is not in O, only by using the definition of the Pn evaluation ring O. And we have also seen that evaluation ring contains the full constant field and there is no algebraic element inside of P without zero. In order to see how this proposition looks like in an example, let me consider the rational function field k of x and the evaluation ring, which is determined by an irreducible polynomial p of x. And here note that in this case, the units of O contains the fractions f over g. Both are not divisible by p of x. Because that means that f over g and its inverse in OPX, and by the definition of OPX we can see it. And in this case, the maximal ideal P contains fractions from O. That means denominator is not divisible by p of x, but they are not unit. So that means f of x is a multiple of p of x. And by using these definitions, you can easily check that f over g in P if and only if g over f is not in OPX, and the full constant field lies in OPX because all algebraic elements, they are not divisible. In this case, we have k tilde is equal to k from the first lecture, and the non-zero constants cannot divisible by an irreducible polynomial. And similarly, with the same argument, there is no algebraic element inside of P. Here, intuitively speaking, we can say more about the structure of these places and evaluation ring. And the first observation, for the moment without clarifying it, my claim is that P is indeed generated by the irreducible P of x. So that means it is a principal ideal. And moreover, we will also see that evaluation ring is a principal ideal domain, and explicitly we will see that the every ideal in OPX can be generated the powers of the generator of P of x. Here n is bigger than 0. And we can also observe that any element in a rational function f over g can be written uniquely as px to the n times ux. Ux is unit in OPX star. And in order to generalize these three observations over this example, we will need to prove a lemma Sorry for the mess. Which says for a given function field f and a given valuation ring with its unique maximal ideal P, when we have a sequence of length n and of elements in P that satisfies this property, so that means we have sequence of elements x1 up to xn such that x1 in element x2 times P, x2 in x3 P, and so on. Then the extension degree of an algebraic function field over K of x, here x is the first entry of the sequence, is finite, and it is bounded below the length of such a sequence. In order to see that this extension degree is finite, it's enough to note that if we have this x, this is the same element in P, it cannot be algebraic. That means x is transcendental. And from one of your homework, we know that this extension degree is finite. And the vector space dimension of f over Q of x is bounded below n, and to see that it's enough to see if it's enough to prove the elements in this sequence x1 up to xn are linearly independent over Q of x. Then we can say that this extension degree is bounded by n. With xi in xi plus 1 times p are linearly independent over K of x. And as usual, we will prove it by contradiction. That means we suppose that they are linearly dependent. So that means there exist non-zero functions such that this linear combination is trivial. And without loss of generality, we may suppose that these coefficients are polynomials, because otherwise, if we have fractions, we can make denominator equal and we can manipulate this equation we can rewrite this equation with some polynomial coefficients. And again, without loss of generality, we may suppose that not all phi ix is divisible by x, because otherwise we can take the x parenthesis and we can apply the cancellation. And here observe that if phi ix is not divisible by x, its constant term is 0, and we can write phi of x is for some polynomial gi of x times x plus ai. And here also note that in the summation, we can consider a term, or we can choose an index j, such that whose coefficients, polynomial coefficients phi I of x is not divisible by x. Phi ix is not divisible by x, and the other terms other coefficients are divisible by x. So that means we can write phi ix gix times x, and here we can write phi j as gjx x plus aj with non-zero aj. So by applying these equalities in this equation, we get this form. And here we want to multiply this equation by xj inverse, because this x1 xj inverse, the coefficient, the terms in this multiplication is element in P, because we have chosen this x1 up to xj minus 1 from the sequence of x1 up to xn that satisfies this property. And here also note that these polynomials are also element in evaluation ring O, because k lies in O and x in O. This shows us the all terms, the all summations here is in P. On the other hand, this polynomial also is an element evaluation ring, and this multiplication is also in evaluation ring. And since x in P. This summation also an element in P. And for the J term, we have this cancellation. And again, with the same argument, we see that it lies in P. And this gives us, if we remove the constant term AJ, now the constant term AJ on the right-hand side, we have seen that in this term also is an element in P. But this gives us contradiction because P intersection K is trivial. And this shows us that such a sequence, the elements of such a sequence is linearly independent, are linearly independent over K of X. This is why this extension degree bounded below N. And in the next video, by using this statement, we will prove that P is principal ideal, O is principal ideal domain, and every other element in a function field can be represented in terms of the generator of the maximal ideal P. So see you in the next video.